Hey guys, Ballet25 here, watching the launch of Vega with Lisa Pathfinder. The broadcast will begin in 40 seconds. Should be interesting. It's dark in French Guiana, so maybe we'll get to see someone's booster subs. Stage set for Vega. I won't be doing too much talking because, of course, it's quite far in the morning, so I won't be. But yeah, there we go. Beginning of the broadcast, I hope.
Ladies and gentlemen, welcome for the 11th launch of the year from the Guyana Space Center. Today's mission will use the last-born vehicle of our family, created by the European Space Agency in the frame of the last launch of Vega Research and Technology Accompaniment VERTA program. Vega is set to deliver Lisa Pathfinder into an elliptical orbit inclined at about 6 degrees above the equatorial plane, with a perigee altitude of 207 kilometers and an apogee altitude of 1,540 kilometers. It will then travel to Lagrange point L1 using its own propulsion means. From liftoff until spacecraft separation, the elapsed time will be slightly above 1 hour and 45 minutes. Lisa Pathfinder is a technology demonstrator which will test the innovative instruments required for the detection of gravitational waves. It should pave the way for implementing space observatories in the future able to detect such gravitational waves and thus verify Einstein's prediction through its theory of relativity. Lisa Pathfinder has been designed and manufactured by Airbus Defence and Space and is the 100th manned payload to be orbited by Arianespace with its launch vehicle family. I would like to thank warmly the European Space Agency for its Arianespace in its science endeavors, as thrilling as those at stake tonight. My gratitude also goes to our prime contractor, ELV, a company jointly owned by Avio and the Italian Space Agency, for ramping up so efficiently in Vega's production and so supporting our increasing launch rates. But the 6th Vega is now being readied for launch, so enjoy the show.
Hello and welcome. We are live at the launch pad here at the Guyana Space Center for the 11th launch this year. We're flying on board Vega, the baby of the launch family, and there it is on the pad, going through the final preparations. And launch is scheduled for just over 16 minutes' time. You can see the countdown there on the top right-hand side of your screen, and those status panels were all green, so we are go for launch. We're using several control rooms tonight. This is the Mission Control Center here at the Guyana Space Center, and here you can see the operational teams in the fishbowl behind me and our VIPs watching tonight's show. And we do have another control room, another important control room, and that is ESOC, the European Space Operations Center. That's in Darmstadt in Germany, and these are the teams who will be taking control of our satellite once it has launched. Our program comes to you in both French and in English tonight. And my friend Thierry Bouvard is in the French commentary box. And we are launching a very, very special satellite. LISA Pathfinder for the European Space Agency is going to help us find out about gravitational waves. We're using Vega tonight, the baby of the family, as I said. She's made of 4 sections. The first 3 are the solid rocket motors, and their job is to get us away from the gravity of our planet. That is the powered phase. And then we have an upper stage, which is called Avum or Avum. That's the 4th stage, and that's the smart section of the launcher. Houses the computer and the avionics, and it can switch its engine on and off. And then this is the fairing, the pointy bit at the top. And inside there you can see LISA Pathfinder for the European Space Agency, built by our friends at Airbus Defence and Space, weighing in at just under 2 tons. 14 minutes and 37 seconds to launch. Our status panels are all green. On the right-hand side of the screen there you can see them, those boards sending their status to the Mission Control Centre, a little bit like a dashboard in your car or indeed a set of traffic lights. Red is stop and green is go. So we have various different teams working here in the Mission Control Centre. This is the Flight Directorate, headed up by Stefan Israel, the Chairman and CEO of Arianespace. This is Arianespace top management. They are the highest technical authority for launch operations. And these guys have the final say in the case of any unplanned situations, and teams working across the base report directly to them. Now, LISA Pathfinder is a very, very important program for the European Space Agency. It's called a technology demonstrator, and it's testing technology for a future mission to detect gravitational waves. Over now to the Director General of the European Space Agency, Jan Werner.
Good morning, ladies and gentlemen in Kourou. Unfortunately, I cannot be with you this time. Also, this mission is a very special mission and is inspiring me very much. LISA Pathfinder, the precursor of LISA, and I hope that we will have LISA also in the near future. LISA Pathfinder is there to show a technology which should finally discover and evaluate the effect of gravitational waves in the universe, going back to Einstein's theory. At the same time, when we have these very inspiring scientific missions, and I'm sure the scientists will explain it later on in detail, we have the Verta launch, the 6th out of the Verta launch with Vega. Vega, our smallest child of the European launch family. So therefore we have both. We have the Vega launch and we have LISA Pathfinder, both inspiring moments of ESA as being a European Space Agency, not only for benefit of citizens in the day-to-day work, but also for inspiration for the future.
Jan Werner there, the Director General of the European Space Agency. Well, it was 100 years ago yesterday that Albert Einstein published a paper that would revolutionize the way we think about our universe. It was, of course, the theory of relativity. In it, he made a number of predictions, and unbelievably, over the 100 years, we've discovered they were all true. Quite an incredible brain. But there's one that we haven't yet been able to verify, and that is the existence of gravitational waves. He called them ripples in the fabric of space-time. Well, LISA Pathfinder is the first step in our quest to discover those gravitational waves. And joining me to tell us more about it is the Director of Science, Alvaro Jimenez. Thank you very much indeed for coming to the floor.
Thank you.
What's LISA Pathfinder going to do?
Well, as you said, LISA Pathfinder is going to be the first step toward our understanding of the universe in gravitational waves, to observe gravitational waves and try to know more about our universe. And I have to say, for centuries, we have been observing the universe in visual, in a very narrow area of the electromagnetic spectrum, and with that we made a picture of what we know of the universe, like having a picture in black and white. Then with the space we managed to get observations of the universe in infrared, X-ray, gamma rays, so we got the picture of the movie in color. Now with LISA Pathfinder we're opening the way to get sound in this movie, because we will listen to these ripples, these variations in the space-time that gives us information totally in a different way about how masses move and behave in the universe.
So it's a little bit like putting a microphone onto the universe.
Yes.
Well, LISA Pathfinder is, of course, a very important mission, but it's one of a number of fantastic missions that the European Space Agency has under its Cosmic Vision program. Tell us a little bit about those.
Well, we are having in a science program a number of missions, and we have three essential objectives. The first one is to understand our neighborhood, our solar system, and we do that with missions like Rosetta, understanding comets, but also missions that we are preparing to go to Mercury, missions we have around Mars, or new missions that we are developing to go to the icy moons of Jupiter. The second objective is to understand the universe, to see stars, galaxies, cosmology, how it all behaves, how it evolves. Looking, for example, we are preparing a mission to look for the nature of dark energy, to understand this element, this component of the universe that is so enigmatic still. And the third, and that is a very important objective also, is to understand the laws of physics that underpin the whole behavior of the universe. And these laws of physics include, of course, gravity, which is the dominant part in the evolution of the universe. And LISA Pathfinder is actually finding the way to get this information about these laws of physics.
And I think it's fair to say, Alvaro, that some people have spent their entire professional lives working on this mission. So today is truly a big day.
It is indeed a big date, and I think it is so great to see that we have now this here ready for launch. And is a big development that, in my view, put together two elements. It's the creativity and the ideas of the scientific community, the scientists involved, together with engineers that make them feasible, that make them true. And how you make true the dreams of the scientists is a teamwork of engineers and scientists together to achieve things like this one we are going to witness today.
Let's find out now, thank you very much indeed, about the launch campaign and the preparations for today.
Coming from Italy, the Vega stages arrived in French Guiana last July on board Toucan on Colibri. Most elements were transferred to the Vega launch pad after being prepared in their respective integration buildings. First to be erected was the P-80 stage after it had been filled with solid propellant in September. The Zefiro stages were added in October, Zefiro 23 and then Zefiro 9. Finally, Avum was mated on top of the other Vega stages end October. LISA Pathfinder spacecraft landed at Félix Éboué Airport on the 8th of October. Mechanical and electrical checks were performed during 1 month on both the propulsion module and the scientific module. The spacecraft was fueled with propellant early November, and then LISA Pathfinder was ready to start the combined operations with the launcher. At D-3, the dress rehearsal took place with the range, the launcher and LISA Pathfinder, and with all the tracking stations involved. On D-1, after final checks, the launch readiness review gave the final go to enter into the launch countdown.
This mission was demanding in terms of performance, and that's why we had to design and optimize the trajectory in order to to get the maximum performance for this mission. And to do this, we had to implement 2 boosts of the upper stage, of the AVOOM stage, in order to reach the performance that was asked for this mission. So the first part of the mission, the PAT, the Z23, the Z9, and first boost of AVOOM, the upper stage, is a standard process which will be followed by Galileo Station, which is the present station here, Natal in Brazil, Ascension in the Atlantic Ocean, and then Libreville and Malindi, which are in Africa. So after the end of the first boost of AVOOM, we have a ballistic phase, which lasts about 1 hour, during which the launcher is placed in a barbecue mode in order to limit the thermal effect of the sun exposition. And then we have the second boost of the AVOOM over Panama, which will be followed by the SNA, which is a naval station on the sea, in the Caribbean Sea. Then we have a short ballistic phase before the separation of LISA Pathfinder. So this separation will be followed by this present station after a complete turn around the Earth, and also by the Diane station, which is used by ESA to follow the first maneuvers of LISA Pathfinder after the separation. And then we have the third boost of AVOOM, which occurs after the separation of LISA Pathfinder and is dedicated to limit the lifetime of the upper stage in orbit after the end of the mission.
À tous de DDO. Attention pour la séquence finale lanceur. Top. H0 moins 4 minutes.
And we have the Range Operations Manager there has just announced the beginning of the synchronized sequence, the last 4 minutes during which the computers are controlling all the final operations in the countdown. Well, I'm joined in the commentary box by Dr. Paul McNamara. Paul is the project scientist for LISA Pathfinder. Paul, thanks so much for joining us.
Thank you very much.
Paul, what is a project scientist?
So the project scientist is, or my role is to manage the science of the mission. So I work both with the engineering team who are building the hardware and with the science team who are actually going to start using it when we launch.
Well, we're very lucky to have you because you're an expert on gravity and the nature of the universe, and you've spent many, many years working on this. So
yes.
Thank you very much. We've been looking at mission control, but we do have other control centres, as I said earlier. This is launch control. There are several teams working in here. One is responsible for all the operations on the ground. They coordinate with mission control for the
Right then. Let's make a bullet, so don't restart that. We still have a bit of time until. There we go. So the internet started to crap up a bit.
Important people here in mission control. This is Jean-Christophe Delaunay. He's the mission director, and he coordinates the day-to-day activities at the launch pad. And then we have the Range Operations Manager, who you saw earlier, John Haar, or Jon. He's Norwegian, and he's in charge of coordinating the launch base systems during the final countdown.
Attention pour H0 moins 1 minute.
We're going to be hearing his voice throughout the flight.
Top. H0 moins 1 minute.
We are 1 minute to launch. We're orbiting the trailblazing gravity hunter Lisa Pathfinder. Airbus Defence and Space. And of course to everybody in ESA's control centre, ESOC, who are waiting to take charge of their spacecraft. Our very best wishes and good luck as we watch the launch.
T-minus 30. 25. 20.
À tous de DDO.
15.
Attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Top. Allumage et décollage de VV06.
There she goes.
Tous les paramètres à bord sont normaux.
And there she goes. We are off. Vega lit up the light night sky there momentarily as it disappeared behind the clouds, heading up over the Amazon rainforest and heading out over the Atlantic
Acquisition
Ocean.
par la station télémesure de Saint-Georges.
Here on the equatorial coast of South America, we're now heading east towards Africa. And Lisa Pathfinder has started her journey. Vega is powering its way across the sky using the first stage there. And we can hear the sound as it arrives here
Les
at
paramètres à bord sont normaux.
the Mission Control Center. He's telling us that everything is going according to plan. And we can hear it rumbling across the sky. We're burning the P-80 first stage here. 80 is the mass of the propellant, 89 tons. And the first three stages are the propulsion phase, getting us away from the gravity of the Earth. Gravity, of course, being the very thing that Lisa Pathfinder is going to be helping us to investigate. On the bottom of the screen, you can see on the left-hand side is our altitude, 47, 48
La trajectoire est
kilometers.
nominale.
He says everything's normal. The distance from the pad,
Séparation du P80.
and the bottom right-hand side is our speed in kilometers per second.
Allumage du moteur Z23.
So we've lost the P-80 first stage. It's burnt its propellant. We don't need it anymore. It's fallen away, and we are shedding weight. We've ignited
Tous les paramètres à bord sont normaux.
the Z23 second stage. That's going to burn for about 1 minute and 30 seconds. Z means Zefiro, which is Italian for a type of wind, like the Sirocco or the Mistral. And of course 23 is the amount of solid propellant that is contained inside the tank. It burns 23 tons of propellant in 1.5 minutes. You can see the fairing is the nose of the vehicle. If you look at that image there on the right-hand side of the screen, that's CGI
Les
image
paramètres à bord sont nominaux.
of what's happening in space. The fairing is the nose. You've got a good look at it there of the vehicle, the pointy bit at the front. That's protecting our satellites from the rigours of the launch, notably the acoustic vibrations at liftoff. Very loud, you can just imagine. And of course friction, because we are flying through the dense part of the atmosphere right now. That's about 120 kilometers
Séparation de l'étage Z23.
and we're coming to the edge of it now. We've lost the Z23 engine and we're about to switch on the Z9.
Allumage de l'étage Z9.
There we go, and Paul has
Séparation de la coiffe.
just come back. Paul, we've lost the fairing, we don't need that anymore. You saw the launch, and now you can see your baby for the first time exposed to space. How are you feeling?
It's hard to put words into. When you see that light up and it just starts to rise into the air, knowing that our little satellite is sitting in there is just unbelievable.
You've worked hard for this for many years.
It's fantastic.
Just everybody look at the right-hand side of the screen. You can see the satellite there with a flat section at the front. Paul, can you just explain to us what we're looking at?
Sure. The flat part we're looking at there is the solar array. That's how we generate all the power on the satellite. Being in space, the only way to get power. Out to our final orbit towards the Sun, towards 1.5 million kilometres from Earth.
And then to the left of that you could see the upper stage there and the Vega launcher. So this was 5 minutes and 17 seconds ago. Paul, what was it like? It went behind the clouds pretty quickly?
Still, we saw glimpses of it as it was going up there. It felt like I was back in Scotland with all the clouds all over the place, but even still, it was still amazing just to see that bit there where it just lights up the sky. It's phenomenal.
It's quite something, and of course Vega flies very quickly compared to some of the larger launchers, so people who are used to seeing the Ariane launcher take off, that
am I supposed to hear that?
is a lot heavier, of course, so it's a slower moment. So here we go. We are 5 minutes now. Coming up to 6 minutes into the launch, and we've switching off the Z9 engine. Don't need that anymore.
Burning out because it's an SIB.
Lisa Pathfinder at the front there on its journey. It's quite a revolutionary.
Acquisition de la télémesure lanceur par la station de Natal au Brésil.
Okay, so we've picked up the signal at the tracking station in Natal. That's on the northeastern coast of Brazil. You can see our flight path there taking us out across the Atlantic. Yeah, I was just saying it's a quite a...
Séparation de l'étage Z9.
And there we go. We've lost the Z9 engine there. So we're coming up now to the next phase in the flight. The main propulsion phase is over. We've got ourselves away from the gravity of the Earth, and we're going to start the next phase, which is
Début de la manœuvre d'orientation avant le premier boost AVUM.
To drop off the satellite in the correct position. And here you can see that the AVUM upper stage is starting an orientation phase.
Tous les paramètres à bord sont normaux.
I was attempting to talk about Lisa Pathfinder there. She's quite revolutionary, isn't she?
Yeah, Lisa Pathfinder is the first step of observing the universe in a whole new way. It's not using light, it's using gravity.
De la télémesure lanceur par la station de Saint-Georges.
So Lisa Pathfinder is essentially a physics lab in space, allowing us to test the technology.
De l'AVUM.
Sorry, it's allowing us to test the technology required to build a large gravitational wave detector in the future.
And we've just switched on the engine of the AVUM upper stage. Paul and I say AVUM because we're Brits, but a lot of Europeans and French in particular who are in control of this particular launcher are calling it the AVUM.
Yes.
Panne de visibilité du lanceur par la station de Galileo.
And we picked up the signal there at the Galileo tracking station that is at the Guyana Space Center. So Lisa Pathfinder is heading off to a position in space which is 1.5 million kilometers above the Earth, and the AVUM's job is to take it there. It's going to take 2 months to get there. It's really blazing a trail, isn't it, Lisa Pathfinder? But we can only test the technologies that she's going to test in space. Why is that?
So what we're trying to do with Lisa Pathfinder is to put a body into free fall. Really what that means is there's no forces acting on it apart from gravity. Now if we were sitting in the Earth, then Earth's gravity would actually wipe out what we're trying to measure. So we want to be outside so we can't even see the Earth or the Moon or any other forces. So the only way to do that is to go into space.
And that's where we are headed now. You can see on the bottom left-hand side we're 264 kilometers high. The distance in the middle is the distance from the pad. Let's find out a little bit more about LISA Pathfinder.
Before trying something new, you need to test the technology first, and that's exactly what LISA Pathfinder will be, a technology demonstration mission. It will become the first gravitational laboratory in space for fundamental physics, and it will test the technologies that will be needed to detect and measure gravitational waves.
Gravity is the fundamental force of the universe. At the largest scales of talking about stars, galaxies, the universe, they're dominated by gravity. So we have to actually look at the ripples in space-time. We have to look at the effect of gravity over all of space.
Gravitational waves from an exploding star, for instance, travel across the universe almost unimpeded, unlike light, which gets absorbed by gas and dust. When they pass through the Earth, they produce minute changes in the size of our planet, but only by about a millionth of the size of an atom, making them extremely difficult to measure. This means ensuring that any detector is isolated or shielded from all other forces which could disturb the measurement. And if you want to investigate gravity, you need something to fall. So inside LISA Pathfinder, there will be 2 small gold-platinum cubes in freefall. The aim is to show that something can be built that is free of all forces except gravity, and is sensitive enough to measure the tiniest of movements caused by the passage of a gravitational wave. A precision micro-propulsion system with tiny thrusters will keep the spacecraft in perfect position. This way, for instance, it can oppose any solar radiation force, protecting the cubes from the external noise of the solar system. When LISA Pathfinder proves this innovative technology, the next step will be another much bigger mission, involving up to 3 spacecraft separated by 5 million kilometers, with cubes in each one. Measuring the distance between them and the gravitational waves that produce any changes in that distance will open a new window to our gravitational universe.
LISA Pathfinder is a first for ESA in that it's a mission looking into a new science altogether, a new way of doing astronomy.
And this new era in space science, first predicted by Albert Einstein almost 100 years ago, will change forever how we see the universe around us.
What an incredible last image, Paul.
Yeah, that's a black hole swallowing matter. That's what we're looking for.
Unbelievable. Now the cubes are going to be in free fall, but what are they going to be falling to? Where is down in space?
Fin de visibilité nominale du lanceur par la station de Natal.
So in space, there really isn't an up or a down, but what we can really say is we're falling towards the sun. We're in orbit around the sun, so that's really our gravitational source.
Now, we talked about general relativity
Tous les paramètres à bord sont nominaux.
Everything's going well. As I said, it was 100 years ago that Einstein published his theory of relativity. What did he predict?
So general relativity is a fantastic theory because not only was it able to explain some measurements we'd already seen, some observations, it also predicted things for the future. So that it was able to explain why the orbit of Mercury continually changes, but then it was also able to predict the fact that light bends around the sun, which was verified a few years later, and also something called gravitational redshift, which anyone who's watched the movie Interstellar will be familiar with, that when you go to a large, massive planet or a black hole, time slows down.
Well, absolutely, and it's a great movie, and I've often wondered how true it was, so it just shows that it is. And we've been trying to work out exactly what a gravity wave is, so we gave Paul a bit of cloth, a cube and a marble to explain.
De propulsion à boom.
So here I have my representation of the universe. So for everyday life, our universe is flat. We drive along the cars, we walk along the street, we have a flat universe. But then Einstein came along and he said, well, that's not quite true. The universe itself is actually like a fabric, and everything which is in the universe creates that fabric to change its shape. And I have here, this is a dummy of a LISA Pathfinder test mass. So this is 46 millimeters on a side. It's made of tungsten, not gold platinum, but it weighs about 2 kilograms. So if I use this to represent my black hole, and I put my black hole into my universe, you immediately see that space changes, space warps around the black hole. And I now have my marble, this is my little planet, or my other black hole, and I let it go round. You start to see that it orbits, and it orbits quite slowly, then it gets faster and faster and faster. And just before it gets to the bottom, if we do it again, if we look at the black hole, you see the black hole starts to oscillate. And it's this oscillation which then creates the ripples in space which are coming out through the universe, and these are the gravitational waves. And these are the things we're trying to measure with the future gravitational wave detectors, of which LISA Pathfinder is the first step.
Well, it certainly helps when you demonstrate it like that.
Okay.
But is this the same force that makes us stick to Earth?
It is the same gravitational force. Another analogy we sometimes use is if you imagine a pond full of water, and the water is the gravity, and I then drop a pebble into the pond, you see the little waves coming off, the ripples, and those ripples are like the gravitational waves. So yes, it is like the gravity on Earth, but we're looking for these little ripples sitting on top of the gravity.
Now, there are some experiments already on Earth, aren't there? Although this is the first time we're going into space to look for gravitational waves.
That's correct. We've actually been looking for gravitational waves on Earth since the 1960s. Yeah, so we've been looking for gravitational waves since the 1960s, and the original detectors were very large bars of aluminium, and it acted like a bell. So when a gravitational wave passed over, the bell would ring, and we would look for these tiny changes in the size of the piece of aluminium. And that then evolved into using laser interferometers. Again, measuring distance, but now doing it by lasers. And today we have several interferometers on the planet. There's 2 in America, which are 4 kilometers long, 1 in Italy, which is 3 kilometers, 1 in Germany, and 1 in Japan. And as a network, these detectors are really right on the edge of making the first gravitational wave detection.
So this is exciting stuff. We're coming up to the next phase now in the flight. The cut-off of the Avum upper stage. It's switched its engine off. You can see there we're at a speed of 7.29 kilometers on the bottom right. And we're starting the orientation maneuvers. Now, this is the first of 2 ballistic phases. Paul, what does ballistic mean?
So a ballistic phase really just means there's no propulsion. So we're now just travelling at roughly the same speed we were when we cut the engine off.
And our flight path takes us east along the equator, across Africa, Southeast Asia, the Pacific Ocean, and back here to South America. So we do a full lap of the Earth around the equator. We're going to deliver LISA Pathfinder quite literally over our heads at the CSG. Now, this team received the information from the tracking stations as it flies over. It's called CVI, or Real-Time Visual Control, and they receive that information. It helps them to check how the flight is going in real time, and they can analyse it afterwards to see how everything went and make improvements in the future if necessary. Now, as we've seen, LISA Pathfinder is made of and will be testing brand new technology. It's quite revolutionary stuff. It's never been done before. It was built by an expert group of European industries led by Airbus Defence and Space in the UK, and it's no mean feat designing and building a trailblazing gravity hunter.
Fin de visibilité nominale du lanceur par la station d'ascension.
Katie, I would also like to add that the Airbus Defence and Space teams have done an amazing job to get us here today. Some of these people have been working many months away from home doing all the testing of a spacecraft and then almost immediately flying out to Kourou to build and make sure everything is working so that, as we see, we have a very successful launch.
And the teams have also worked well on the launcher side. Not only is Vega the smallest of the Ariane family of launchers, she's also the youngest. This is her 6th launch in total and her 3rd launch this year. So we are meeting expectations. Vega is a European Space Agency programme. She's built by the Italian company Avio for the prime contractor ELV.
The launcher meet the customer needs. So when it comes to the future of access to space, Avio is there.
Okay, whatever you said.
21 minutes and 54 seconds into the flight. Paul, we're heading to, we've heard about this Lagrange point. We're heading to Lagrange point number 1, depending on how you pronounce it, a point between the Sun and the Earth. What is it?
So Lagrange points are special points in space. So if you take a two-body system like the Sun and the Earth, there are 5 Lagrange points.
Acquisition de la télémesure lanceur par la station de Malindi au Kenya.
And the Lagrange points are special in that the gravity from the Sun and the Earth doesn't exactly cancel, but it does give us a point where if you place a body there, it will orbit the Earth in exactly 1 year.
After separation from Vega, we will switch on the spacecraft radio, what we call the transponder, to send telemetry and receive telecommands from the 16 minutes later, the propulsion module is ready to be used. And a few minutes after that, the spacecraft will automatically point its solar array towards the Sun. By day 3, we will calibrate the performance of the main rocket with great accuracy by means of a test burn. Then, a series of 6 fires of the main rocket, when the spacecraft is closest to the Earth, will increase the size of the elliptical orbit until, with the last one, LISA Pathfinder will start its trip towards the Lagrange point in the direction of the Sun. About 50 days after launch, en route to the Lagrange point, the propulsion module and the science module will separate, and the science operations will commence.
So that's what's going to be happening during the launch and early operations phase. And as we mentioned, the teams overseeing all these operations are based at ESA's control centre in Darmstadt in Germany. ESOC stands for European Space Operations Centre. They effectively fly the satellites and they control all the spacecraft in ESA's space science programme. And they receive the scientific data from those spacecraft. So they are doing a hugely important job. And right now they are waiting to take control of LISA Pathfinder. What are they doing? We can see them here now. What are they doing, Paul?
They look very relaxed, which is nice to see. The teams have been training for many months for exactly this period, and now we're seeing the fruition of that, where they know exactly what to do, when things will happen, and they're relaxed with it. It's very nice to see.
So we'll be coming back to the teams there in ESOC over the during the flight, and hoping to chat with them a little bit later on in the flight. We are at an altitude here of 676 kilometres above the Earth. Why does LISA Pathfinder take 2 months to get to the Lagrange point?
I think the simple answer to that is it's quite far away. It's 1.5 million kilometres to get there. But to make life even more complicated, because we're on the small launcher Vega, we get dropped off in a parking orbit close to the Earth. And then we have to, as Cesar mentioned, we have to continually boost the orbit until we get to a transfer out towards our Lagrange point. So we just have to travel a long way.
So we're travelling now at just under 7 kilometres per second. We're in the ballistic phase. We are 25 minutes and 37 seconds from that launch. You were there, Paul, watching it with your own eyes?
I was. It was quite far away. We're about 12 kilometres away. But even that, it just lights up. That's the best way to describe it. And then you don't hear anything. It's very quiet until the rocket was overhead. Then you really hear that rocket engine firing.
You can actually feel it. You can feel the ground shaking.
Yes. Certainly not something I'm going to forget.
It was certainly a perfect lift-off and a beautiful sight. So we're going to come back to you now in a little while, because we have what we call our ballistic phase. It lasts... Avon's going to switch its engine back on in 1 hour and 15 minutes to start the process of delivering the satellite. And so we're going to take a break, and we'll be back just before that in about 1 hour and 11 minutes. The times in French Guiana, that's 1:04 in the morning. Greenwich Mean Time, or Universal Time, is 4:04, and in the rest of Europe it's 5:04.
I won't end the video here. Not end the video, pause the video until the whatever you say it, until the second, well, until the other guy's return. So, see you guys then.
Space Agency. It's going to be testing brand new technologies for a future mission to hunt for gravitational waves in the future. We are 1 minute and 38 into 1 hour and 38 minutes into the flight, and we'll shortly start releasing our satellite onto its orbit. I'm Katie Haswell, and joining me is Paul McNamara from ESA. Paul is the project scientist for the LISA Pathfinder program. We're going to relive the launch, which Paul watched. Paul, talk us through what we're seeing here.
So here we have the blast off. Absolutely fantastic sight. The whole sky just lit up as if it was on fire. We managed to go for a few seconds, and unfortunately we hit the cloud layer, but even then it was still such a fantastic sight. And then we were very fortunate. We actually understood just how fast the rocket was travelling when we saw little gaps in the cloud, and just how quickly this thing shot across the sky.
And here we're seeing it from different angles. We have our cameras in the different viewing stations around the Guyana Space Center. Look at that firepower blasting out. Vega pushing itself away from gravity there.
And when we see this, we realise that our delicate instrument is sitting on top. It brings a whole new meaning to why we have Airbus Defence and Space, who spent so much time and effort testing the hardware to make sure it would survive this.
Acquisition de la télémesure lanceur par la station navale SNA, située au nord de la Colombie.
So we've now picked up the signal at the tracking station at SNA, which is the north of Colombia. And there you can see some of the stages of the flight. The various parts fell away. The Avon took over, Avon being the upper stage. There's LISA Pathfinder at the front there, and it then switched its engine off. We had a coast phase, And we're now back again, getting ready to launch. Separate LISA Pathfinder onto her orbit. So we've done a full lap of the Earth along the equator.
Yeah, and we're just about made it all the way back round again. We're now just approaching South America, and very shortly we'll be back over Kourou, where we will separate from the upper stage of the launcher, and then LISA Pathfinder will be on its own after that.
And we'll be separating right over our heads, which is something that we've never done before.
I certainly haven't.
So, as I said, we picked up a signal at the Station Navale Ariane, which is a boat, and that's going to be tracking separation. The Avum upper stage is scheduled to switch its engine on right now, and you can see that on the picture there.
Allumage de l'Avum.
And we have confirmation that the upper stage has switched its engine on, bang on schedule. It was developed by a Ukrainian company called Yushnoye. I think I've pronounced that correctly. And he's telling us that the parameters on board are normal. Everything is going according to plan. Avum can switch its engine on and off a number of different times, and it's designed to inject different payloads to different orbits. How is that useful, I mean, particularly in this mission?
Well, if we take the Vega launcher, it's a small launcher designed to launch maybe 1 or 2 satellites. And for other... I think we just told everything's wonderful down there, so that's very nice. But most of the small launchers launch maybe 1 satellite. With Vega, we can launch several satellites where we use the Avum to put the first one into its orbit, we jettison it, then we can fire the Avum again, go to a different orbit and send the second satellite. So it gives a huge flexibility to the launch vehicle to launch multiple payloads.
And it's the smart stage. The lower module has the propulsion, 4 tanks containing 2 types of liquid propellant, and the upper module contains the avionics. That's like the cockpit of an aeroplane, the flight control systems, navigation, communications.
Extinction de l'Avum.
So Avum has switched off its engine. Avum or Avum, depending on how you pronounce it, has switched off its engine for its second ballistic phase, and we are now on orbit. Paul, tell us where we are.
So we're now 218 kilometers.
Début de la manœuvre d'orientation au profit de LISA Pathfinder.
So we're 219 kilometers above the surface. We've travelled, we're actually about 2,100 kilometers away from the launch pad, and we're travelling at a speed of 7.64 kilometers per second. So it's a very high speed, and we're approaching the launch pad rapidly.
And let's just repeat that, 764 kilometers per second. Phenomenal. We're in what we often call the space ballet, because the upper stage is twisting and turning in a rather balletic fashion. It's getting ready to release the satellite. It's going through a very carefully planned set of maneuvers. We have to orientate the satellite correctly to set it on the right path.
Fin de la manœuvre d'orientation.
He said end of the orientation maneuver.
Tous les paramètres à bord sont nominaux.
Everything is going according to plan.
Réacquisition de la télémesure lanceur par la station de Kourou, Galileo.
And we've picked up a signal at the Galileo tracking station. That is over us here in Kourou at the Guyana Space Center. You can see the white dot there is the position of the launcher. And Galileo tracking station to the east there, another tracking station called Diane or Diane, which is the ESA tracking station. We'll be talking about that in a little while. If you look at the top right-hand side of the screen, Paul, we can see what looks like a roller coaster on our trajectory. We've gone up and we've come back down again. What's that about?
So this is just to do with the shape of the orbit we're in. We're actually in an elliptical orbit, we have an egg-shaped orbit around the Earth. So we started off at 0 on the launch pad, and then we headed out into the top part of the ellipse known as apogee, where we turn around and then head back
Séparation de l'ISS à Pathfinder, vue par le lanceur. En attente de confirmation par le centre de contrôle satellite.
And we have separation of the LISA Pathfinder satellite.
Well, I mentioned the video here, and I can confirm